I am R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this video, we will discuss the topic characteristics of TE and TM waves. So, what do you infer from this diagram? We have the VI characteristics. So, in the similar way, the transverse electric and magnetic waves also some characteristics. So, by examining the field equations of TE and TM waves, we can understand that each component of electric field and magnetic field, there is a sinusoidal or cosinusoidal standing wave distribution across the guide in the x direction, and in the y direction, by assumption, there is no variation of either magnitude or phase of any of the field components. So an xy plane is an equiphase plane for each of the field components, and all these equiphase surface progress along the guide in z direction with the velocity v is equal to omega by beta. Here beta is the phase constant, and it is the imaginary part of the propagation constant gamma. And the propagation constant gamma of a parallel plane gamma is equal to root of h squared minus omega square mu epsilon, because we know the expression h squared is gamma squared plus omega square mu epsilon. From this we can get the gamma value, and h is m pi by a. By substituting the h value in propagation constant gamma equation, we have gamma is equal to root of m pi by a the whole square minus omega square mu epsilon. And here gamma is the propagation constant, it is alpha plus j beta. It is complex quantity. Alpha is the attenuation constant, beta the imaginary part is the phase constant. At higher frequencies, this omega square mu epsilon is always greater than the m pi by value, because omega is the angular frequency. So under high frequency, this term which contain omega value is greater than m pi by a the whole square. So we can write this as gamma is equal to the root of minus of omega square mu epsilon minus m pi by a the whole square. So this minus is taken outside, so root of minus is j. So now the alpha plus j beta value, that is propagation constant value, will have only the imaginary part. So since it is imaginary, we can understand that the real part alpha is equal to 0 and the phase constant beta is equal to root of omega square mu epsilon minus m pi by a the whole square. And what happens is, when the frequency decreased, the critical frequency is reached at which both the values are equal, because at the critical frequency no wave propagation, gamma is equal to 0. So since gamma is equal to 0, we can write root of omega square mu epsilon is equal to m pi by a the whole square. So omega c squared is equal to 1 by root of mu epsilon into m pi by a the whole square. Now omega c is obtained by taking the square root. So we get 1 by root mu epsilon m pi by a, and this omega c is substituted as 2 pi fc. So it is 2 pi fc is equal to 1 by root of mu epsilon into m pi by a. So here by simplifying this, we get the final expression for cutoff frequency fc is m by 2a root of mu epsilon. So from this equation, we can understand that for each value of m, there is a corresponding cutoff frequency below which no wave propagation can occur, because we know that fc is the cutoff frequency, and below cutoff frequency there will not be any wave propagation, and the wave propagation starts only from the cutoff frequency value. And the next characteristics is the wavelength of the TE and TM wave. It is denoted by lambda bar. So it is nothing but the distance required for the phase to travel through 2 pi radians is the wavelength. So lambda bar is 2 pi by lambda. Substituting this beta value, lambda bar is equal to 2 pi by beta is root of omega square mu epsilon minus m pi by a the whole square. Now the phase velocity or wave velocity is the velocity of the wave traveling through the parallel planes it is V is equal to lambda f. Lambda is 2 pi by beta, so 2 pi f in the numerator is omega. So now we can write the velocity by the formula omega by beta. So omega, beta is substituted as root of omega squared mu epsilon minus m pi by a the whole square. So now these are the characteristics of the transverse electromagnetic wave. So far we have discussed about guide wavelength, phase velocity, cutoff frequency, and the group velocity, etc. So now the assessment questions. So what is cutoff frequency? We know the cutoff frequency is the frequency at which the wave motion stops or ceases. So below cutoff frequency there will not be any wave propagation, and the wave propagation starts from the increase in the cutoff frequency. And the relationship between phase velocity and group velocity, it is a well known formula, lambda g lambda ph is equal to it is v square, that is the velocity of light the whole square. And the defined guide wavelength, it is the wavelength of the wave when it is propagated through a guide and or a parallel plane waveguide. And next is what is the relationship between cutoff frequency and cutoff wavelength. We know the frequency wavelength relation. Lambda, the wavelength is c by the cutoff frequency, c by the frequency f. So lambda is equal to c by f. So that we can write the relationship between cutoff frequency and cutoff wavelength is lambda c is equal to c by fc. So this is the relationship between cutoff frequency and cutoff wavelength. So in TE and TM waves, the characteristics are equal for both the waves, and this is about the characteristics of transfer TE and TEM waves when it is propagating through parallel plane waveguide. Thank you.